All right, let me draw a blackboard, and today let's go over an example of Taylor polynomials. Right, so I'm assuming, perhaps incorrectly, that most of you already know what a Taylor polynomial is. But I guess in case you don't, let's go through the definition real fast. So we'll write this Taylor polynomial example. All right. So you might have this function f of x, and it needs to be differentiable essentially as many times as you need it to be. So if you're trying to generate a polynomial of degree 4, then you need this function to be differentiable 4 times. If you're generating a polynomial of degree n, then you need this function to be differentiable n times. So when we look at this, we have t sub n of x. So the t stands for Taylor, obviously. N stands for the degree of the polynomial, and it would be a function of x. Now, typically, problems will say that it's centered about something. So that's basically just saying we're going to start with a guess at the first point, like one single point on the function. Doesn't really matter where it is, but we're going to start from there, and then we're going to begin to match the derivatives. So a Taylor polynomial has this kind of special property of having coefficients that are functionally generated. So they follow a kind of formulaic pattern, and you can actually find them quite easily, and they're all based on the derivative. So typically what you'll see is that, it's c sub 0 and then plus c sub 1 times quantity x minus wherever it's centered. So let's call it a plus c sub 2. So the coefficient in front of that quadratic degree, right? Times x minus a and quantity squared plus dot 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 plus c sub n times quantity x minus a and quantity to the nth power. So this is the general form of an nth degree Taylor polynomial that is centered about x equals a. Now, with that said, the question becomes, how do I actually rewrite this? So I'm going to write this in pink. Actually, we'll choose green. Green on the side over here. So what we'll have is c sub n must actually just equal the nth derivative evaluated at where the center is, a, all over n factorial, right? This is the idea of the coefficient. And if we were to actually plug it in, so we would be able to rewrite this, we'd have the nth degree Taylor polynomial of x centered about a is going to be, well, actually c sub 0 we would replace. We wouldn't take any derivatives, so we just take the function f, evaluated at a, divided by 0 factorial. And obviously this is multiplied by x minus a to the 0th power. We typically don't write this part right here because x minus a, as long as we have that and we raise to the 0 power, should be just 1, right? So if we have this, we can have f prime evaluated at a divided by 1 factorial, and this will be multiplied by x minus a to the first power. And for the second term, the c sub 2 would just be f double prime evaluated at a divided by 2 factorial. So this is the actual coefficient right here, and we would just multiply again by x minus a and quantity squared. Until we hit the general term, it would be f, and when you take the nth derivative, evaluate it at a, and then divide by n factorial. And then, of course, we multiply by quantity x minus a and quantity to the nth power. So with that said, let me give you an example of perhaps something that you might see in a problem, whether it be multiple choice or free response or anything like that. You might be given a common Taylor polynomial. I think that's a little trivial at this point. Or we might have something along the lines of, let's say, 1/2 e to the x squared. Okay. So imagine that you actually have this kind of scenario here. You should know the common Taylor polynomials for e, for sine of x, for cosine of x, for ln of 1 plus x, those kinds of things, right? And let's take a look and try to explore what's actually happening here, right? So e to the x, I would say would be approximately, because we're approximating it using a polynomial, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus, and then it would go on, so on and so forth, right? So again, we can have that, or we can just kind of end it off and just say maybe x to the n over n factorial, right? The way that we would typically write this is in closed form. We would say that e to the x is actually approximated by the summation from I equals, let's say, 0 to n. That's easier for me to write. And we would just write out whatever the Taylor coefficient is, right? So it would just be, in this case, the ith derivative of our function. So function will be e, evaluated at, let's say, 0, because that's where we want to center it, divided by I factorial, and then multiplied by x to the ith power, right? So this whole kind of relationship here can mimic everything that we have above, right? So it wouldn't be too bad to have. But the question becomes, we want e to the x squared. And not only that, we want 1/2 of this. So I want to run a kind of little mental exercise past you. And I'm going to write this in open form so that you can actually see it. What if I were to have e to the a power? How would we actually approximate this? Well, notice that a was just a substitute for x. So on the right-hand side, we should do the same thing. It would just become 1 plus a squared over 2 factorial plus a cubed over 3 factorial plus dot, 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 so on and so forth, until you have a to the nth over n factorial. And so that wouldn't be difficult at all. And if I had, let's say, e to the b power, then I would just replace all of them with b's. And so if I were to have e to the x squared power, then I would just have e to the x squared, and that would be approximated by 1 plus x squared plus, and in this case, I had to replace the a with x squared. So x squared squared divided by 2 factorial. And then plus over here, I would have quantity x squared and quantity cubed over 3 factorial. And then so on and so forth until I get the final term, which is the quantity x squared and quantity to the nth power over n factorial. So that would be what e to the x squared would actually be. And then our function actually becomes really, really obvious. So I'll make it in light blue just to match. Our function f of x that equals 1/2 e to the x squared like this will be approximated by 1/2 of what we had earlier. So e to the x squared, we approximated it down here. So this becomes 1 plus x squared plus, and over here what we have is this quantity x squared and quantity squared all over 2 factorial plus quantity x squared and quantity cubed over 3 factorial. And then we would keep on adding until we get to this arbitrarily large nth term that we would have. So this becomes kind of our new situation. And that way we can actually just simplify it. And so this is still going to be, and if we just do distributive property afterwards, right? 1/2 plus 1/2 x squared plus, in this case, it's x to the fourth. And it's 1/2 times x to the fourth over 2 factorial. So this becomes 1/4 x to the fourth power. And then the next term, well, 3 factorial is just 6. 6 times 2 is 12. So this becomes 1/12 of x to the sixth power. And then we can continue going onward until we get to this final term over here, which would be x to the 2n all over 2 times n factorial. Be careful. Know that the n factorial is done first, and then you multiply by 2, right? So this way, if they were to say, hey, what's the coefficient in front of the x to the fourth term? You'd just be able to say, oh, it's 1/4. Or if they're tricky, they might say, hey, what's the coefficient in front of the x to the fifth term? And then you can confidently know that there is no x to the fifth term, so the coefficient is going to be 0.